All right, everyone back?
Yeah, I'm here.
Okay, all right, cool. All right, so I want to do an example. And I'm going to do it two different ways. I'm going to do it the hard way and the easy way. Part of it is so that you could get an idea of how to do the worksheet, okay? Because in the worksheet, the magnetic fields that are not uniform, so you have to break up the wire into teeny tiny pieces and then perform an integration. I mean, it's not a hard worksheet because the geometry is pretty straightforward, but I just want you to go through the process. And you might see an exam problem on it. So let's say we have, in this example that you see, a wire in the form of a semicircle is carrying 5 amps. And its radius is a 1/4 meter, so it's a big loop. Okay. And we have a magnetic field out of the board. So I'm going to draw a coordinate system. So we have a magnetic field out of the board of 1.8 Tesla. Let me define my coordinate system in this problem. It's X. This is Y. And that's Z. And so the current, let me draw one more arrow for the current, like that. And I'm going to do this the hard way. I'm going to break this up into teeny tiny pieces. I'm going to break it up into a DS. Which points tangent to the circle, the direction of the current. So this is the unit vector represents the direction of ds. And then the magnitude of ds, which is an arc length, how do you get the arc length? What's the equation for arc length?
Radius times theta.
Okay. But if it's infinitesimal, then it'd be radius times d theta, right?
D theta.
Okay.
Yeah.
So let's say that this ds is at the angle theta. I need to also write the unit vector attached to this. And I can determine that fairly easily. So I'm going to make my, to help myself with the geometry, I'm going to redraw the coordinate system here. At least the x and the y directions. Okay. So that if this angle theta, what's this angle?
That one's also theta.
Yeah. And what about this one?
90 minus theta.
Okay. So the x component of this vector, is cosine of 90 minus theta, but it points to the left. And the y component of this thing points upward. And it's opposite, so it's going to be But we know what cosine of 90 minus theta is, right? You all know what cosine of 90 minus theta is, the same as the sine of theta. And And the sine of 90 minus theta is cosine of theta. So that's my ds. And so df is I ds, which is this thing, right? Let me put this here. I'll do the following. I'll let B naught equals (1.8). Okay, I'll put the numbers in later. All right, so I got to work this cross product out first. I'm going to draw a coordinate system. So the first thing I'm going to do I'm going to multiply everything through with a B naught. What's I cross K? I'm sorry, what's minus I cross K? What is that going to be? Put your fingers in the direction of minus I, curl them
Positive y?
Positive y. So it's going to be in the j hat direction. And what is j cross k? Put your fingers in the direction of I, and you got to curl them towards the magnetic field. So it's the I hat direction. Okay, these are all numbers. So then f is going to be the integral I'm going to move the d theta on the other side. And what is my range of integration? I mean, I got to integrate
0 to pi.
0 to pi. So when I integrate, I'm running out of space. When I integrate sine, what do I get?
Negative cosine.
Negative cosine. Okay, negative cosine. And when I integrate cosine,
You just get sine.
okay. Let me focus on the second term. What is sine of pi?
0?
What's sine of 0?
0?
Okay, so we don't care about this guy, right? That one's gone. All right, so what am I left with? I'm left with, let me come over here, sorry. We're left with the force is I, R, B naught. And let's put the limits here. Minus the cosine of pi is 1, right?
Yeah.
So 1 minus negative 1 is 2.
2.
And it's in the j hat direction. So the current's 5 amps. R is 0.25 meters. B naught is 1.8. And then we have a 2. This ends up to 4.5 newtons in the j hat direction. Okay? So I did it the hard way. Now let's do it the easy way. Because the field is uniform, I can write F is I, L, cross B. Now what's L? Well, the current starts here.
Wait, Professor.
I'm sorry?
Is I 5 or is it 50 amps?
5.0.
Oh, okay.
Sorry. So L is the vector that goes from here to here. L points in a negative I hat direction. We already said minus I cross K is J. Can you still see?
Yeah, you're good.
Okay. So I get 5.0 amps times 2 times R. So the minus I and cross with the K gives me J. So I get the same answer. Of course, this was much easier, right? I can use this because the field is uniform. L is the vector that points from here to here. Make sure you use this idea in one of the homework problems. One of the homework problems looks really complicated. However, if you use this idea, it's really easy.
Hey, can I ask a quick question?
Yeah.
So the L vector is basically the displacement vector?
Yeah,
like
that's
from
all
start
it
to
is.
finish? Okay, cool.
Yeah.
Thank you.
That's what made this easy. And as opposed to the way I did it the hard way, right? I mean, really all I did was calculate the displacement vector in that problem. Okay, let's do one more example. This is conceptual. And I'll let you think about it. So I'm going to make this thing a little bit bigger. So you have a wire carrying current. And there's a horseshoe magnet there. And the force on that wire is upward. And we want to write down which side is the North Pole and which side is the South Pole of that magnet. So I'll give you a minute. I'm going to draw the picture while you're looking at that picture. Okay. So, again, we have to apply the right-hand rule. So I'm going to draw my coordinate system. Watch how, I just do it this way. So we have F is up, I is into the board. If B pointed to the right, then I would curl my fingers in the direction of I into the board. And then I have to curl them towards B, but the way my hand is right now, I can't bend my hand this way. I have to turn my hand around. Okay, so I'm going to flip my hand over, and now I can curl I towards B. And my thumb points downwards, so that's opposite the direction of this force, so it can't be this. Right? I'm solving this by guessing, right? if I'm using the right hand rule. If I use determinants, I can do it exactly. I mean, I can do it right away. If I use the right hand rule in this case, I put my hands towards I, curl them towards the magnetic field, my thumb points upward. So the magnetic field goes from right to left, and magnetic field lines go from the North Pole to the South Pole. So this is the North Pole, this is the South Pole. Okay? Questions on that? So here's an interesting application. It's the speaker. Now, this is basically, your speaker, your loudspeaker is basically a special cardboard around a metal frame, and behind it is a permanent magnet with speaker wrapped around. Now, you have loops of wire, but they're in a non-uniform field. And you can calculate the force and everything on that cone. Okay? I'll give you an idea how this works. Basically what happens is that you get the speaker to vibrate. Okay? So I have my own speaker. This is an idea of some past students of ours. So my loudspeaker, and let me get rid of that PowerPoint slide so you can see better. Here's my speaker. This is just a simple speaker. I have a magnet on the outside and a magnet on the inside. If you have a coil of wire, you can try this at home. So here's a coil of wire. I was going to take this cup and put it inside the coil of wire, like so. And so the vibration of the cup is going to produce a sound. It's going to vibrate the air molecules around it, and it's going to produce a sound. So I'm going to turn this power supply on. This is the signal generator that you'll be using when you do the scope quiz. So I'm going to turn this on. This was also the signal generator I used to demonstrate the RC circuit. So let me put in a couple of volts. Let me know if you can hear anything. Uh-oh. I think I lost my mic. Can you guys hear me?
Yeah.
Okay.
Yeah.
All right. So I'm going to put this in. I'm going to put this thing with the magnet in here. Do you hear anything?
I kind of heard something right at first, but it was quite small.
It's not very loud.
Yeah, I can faintly hear something.
And when I take it out, you hear nothing, right?
Yeah.
It's a high-pitched tone, right?
Yeah.
Yeah.
Okay, let me change that. I'm going to change the frequency. Is it louder now?
Yeah.
It's vibrating. These things have different frequencies of vibration, so it'll vibrate more at certain frequencies. That was louder, right?
Yeah, definitely. Yeah.
I mean, it's an ideal speaker. So if you actually connected these leads to your the output from, like, say, your iPhone playing music, you would hear the music. So basically all we're doing is getting the speaker to vibrate at various frequencies. So basically all a speaker is just a magnet and some cardboard in a time varying current. Okay, the current is really time varying, it's alternating. Okay. And the fact that the vibrating cone causes the air molecules to vibrate, that's what's producing the sound, because you have a change in the pressure. And it's really a small change in the pressure. If you take 215, we briefly talk about that it's a really small change in pressure that allows you to hear sounds. Now, suppose that we have a loop of wire in a magnetic field, and whoops. To make things simple, let's make the magnetic field uniform, at least for our discussion. If you make the magnetic field non-uniform, this is a much more difficult problem. So, in the figure, and maybe I'll blow this up so you can see it better. I have a loop of wire in a magnetic field. Okay, the end and the end are the north and the south pole of a magnet. Although we're going to assume that the magnetic field is uniform, the poles, that picture you see really doesn't indicate a uniform magnetic field. But let's ignore the fact that it's not uniform for now. Okay. The black that you see is the loop of wire I'm talking about. And so the current flowing through that wire is going clockwise. Not through the wire, but through the loop is clockwise. Okay? And because of that, the force on each vertical wire is shown. There's no force on the top wire, the top of the loop, and there's no force on the bottom of that rectangular loop because I is parallel or anti-parallel to the magnetic field. The cross product is 0. Those two force vectors are equal and opposite because the magnetic field is uniform. So the sum of the forces is 0, but the sum of the torques is not. And so it's going to cause that loop of wire to rotate. So let me draw the loop of wire. It's carrying current like this. And the magnetic field is that way. Okay? So we have the force on this side going into the board, the force on this side coming out of the board, as you see in the slide. And you can apply the right-hand rule to show that. Okay? So the sum of those two forces is 0 because B is uniform. You just use this equation. But it's going to rotate. It's the same thing as if I took a square plate, pivot it in the middle, and I applied force here, and I applied a force here. They're equal and opposite forces. Even though the sum of the forces equals 0, this thing is going to want to rotate. It's going to want to spin because there's a torque on it. And so what I want to do is derive an equation for the torque on it. Okay? Now, in order for us to do that, I need to look from the top. I'm going to look at the loop from the top. If I look at it from the top of the loop looks like this. So these are the lengths. And this is the width of the loop. Okay? So let's say this thing is at some sort of angle. And so this current, if I look from the top, that current is coming towards us. And this current is going away from us if I look from the top. And I'm going to sum the torques about this point. So there's a force this way on that wire. And there's a force this way. On this guy. Again, we're looking from the top. And I'm going to calculate the torque on this thing. I'm going to calculate R cross F. So couple ways I can do it is torque is just this. R is a vector that goes from here to here, or from the center to this point. If I call this vector W over 2 and this force F, then the torque is going to be W over 2 cross F, but these two are in the opposite directions. And the minus signs cancel. I get that. Okay. And F is ILB. Let me do it another way. Right, this is the F is the ILB. So I'll write it like that. So it's actually hard to determine. It's really hard to look at this in terms of what the direction of the vector should be. Okay, because this is a cross product. Right,
Professor?
Yeah.
For your R being the W vector over 2, that you're just taking the component that's perpendicular to the force, right?
Well, it's this is W, right? This is W over 2. But yeah, that's what I'm going to do in a second, right? The component perpendicular to the force is what?
W over 2 sine theta?
Yeah, so if I do it in terms of magnitude, then I'm going to get the magnitude of the torque is going to be W over 2 times the force times sine of theta, right?
Mm-hmm.
And there's two of them, like that.
I see. Thank you.
Okay. And the force, and this thing is ILB. Actually, in the slide, I'm using phi. But what's W times L?
The area of the
The area. But the torque is a vector, and so is the magnetic field. So we can write this. We can write this as a cross product. We can write it as a cross product. The torque is I times the area vector cross B. What's the area vector? How do you find the direction of the area vector? Well, it's the normal to the loop. Okay. The area vector is the normal to the loop.
And I would imagine, like, if you went through that, it doesn't matter which normal you take.
Ah, good question. It's an open surface, right? How am I going to define the normal to the loop? That's the question. Well, in order for it to be consistent with the direction of the torque, the normal that you take to the loop is defined by the right-hand rule. Okay? So the normal to the loop of current carrying wire defined by a right-hand rule. We'll go with that. So you curl your fingers in the direction of the current. So I'm going to curl my fingers clockwise. My thumb points into the board. My thumb is the direction of the normal I want. Okay? That makes it consistent with the direction of the torque vector. We okay with that? Okay. So the torque on a loop of wire.
Wait, Professor.
Yeah.
For the right-hand rule, then do we point towards the magnetic field?
The right-hand rule for determining
For the
normal?
normal. Yeah. Or is it just two components?
It just the right-hand rule for the normal to the loop. You just curl your fingers in the direction of the current clockwise. Your thumb points in the direction of the normal to the loop. That's
Okay.
it.
All right.
Okay. So then this depends on. So if I write this as a, so this angle is the angle between normal to the loop and the magnetic field. Okay? Now I'm missing something. What if this is 50 loops instead of one loop? Then I should multiply this by 50, right? If this is wrapped around 50 times, then the torque is 50 times as big. Isn't that true?
Yeah.
So I should also include something that takes into account the number of turns in my loop. So n is a number of turns. And we define this product as the magnetic dipole moment. So this thing is the magnetic dipole moment. It's denoted by the letter m or the Greek letter mu. And it's the analog of the electric dipole moment. Okay, it's the analog of the electric dipole moment. And I wish I would have more time to go into more details on this topic, but I just don't. So the torque on a loop of wire depends on the angle between the loop's normal and the magnetic field. The loop's normal tries to align itself with the magnetic field. And again, that product NIA is called a magnetic moment. We either use the letter mu or m for the magnetic moment. Okay, and again, we determine its direction by the right-hand rule. So we can write the torque as m cross b or mu cross b. Most books use mu. Some books use m. Okay. And that's the analog of the dipole moment, the electric dipole moment. Here's a loop of wire in a magnetic field. This is I got for, I'm able to show this in video. It shows you the force on each side of the wire and everything on that thing. Okay. Here's an example of the applications of this idea. In the ammeter, you run a current through a loop of wire. Hold on a second. It produces a force or torque on that loop of wire, causing it to rotate. And there you notice, you see at the top there a spring. And this thing rotates. And so it's calibrated depending on what the torque is on that loop of wire. So that's a simple application of the torque on a loop of wire in a magnetic field. Okay. So we could integrate this and derive an equation for the energy stored by a dipole. If you remember, the energy stored by an electric dipole is minus P dot E. We could integrate the expression, and I did this in class for the electric field. I can do it for the magnetic field. So if you have a dipole in a magnetic field, the energy stored is minus mu dot B. And again, all you got to do is integrate this expression over a range of angles, and you can get this expression. I'm not going to derive it. Okay, you can take a look at your book. The most elementary magnetic dipole is that of the electron. The electron has spin, and it has an inherent magnetic dipole moment. And that spin is really a relativistic effect. So another application of the torque on a loop of wire in a magnetic field is the electric motor. The electric motor is a device that will convert electrical energy into mechanical energy, and you're going to be building an electric motor in your project. Remember, I gave you this kit to build a motor with, and so you're going to be building a motor, although you want to build a fairly efficient one given these directions. Your job is to make it work as efficiently as you can make it. Okay, you want it to run on 3 volts or less. I'd like to see some folks try to get it to work under 3 volts. Okay, especially since you're going to be coming to campus and testing it. So I have a sample model, a large version, a student motor for you. So I want to show you it. So I'm going to zoom in, probably a lot. Let's see. And this darn thing, this scope is in the way again. Let's see if I can zoom in some more. That's the motor. Okay. This is for demonstration purposes. It really doesn't. It's not a very effective motor with real life applications. But this is the device. This actually designed to run as an AC or DC motor. When I disconnect it, I'll bring it closer to the camera so you can take a better look at it. So these guys are called the brushes to make the electrical connection. There are things called, there are motors called brushless motors, but we're not gonna spend time talking about them. And we can spend several lectures talking about motors. Okay. This is also a generator that works backwards, and I'm going to use the same device and show you how it runs as a generator. Really, all it is a loop of wire, this is a loop of wire rotating in a magnetic field. This creates the magnetic field. Okay, I have a loop of wire here around the iron. That loop of wire is going to turn the iron into a magnet. And when I energize this thing, it's going to rotate. So this is actually an electromagnet, so I have power going to it. Okay. And I also have current running through the armature, the loops of wire in the armature. And I'll bring this up closer in a minute. So I'm going to demonstrate this to you. My only problem is the power supply I'm using. I cannot really, I would like to go to a lower current voltage setting, but I cannot. I don't want to run too much current through it. And so it spins by itself. I've actually got 7 amps going through this thing and only 2 volts on it. As a result, it's spinning pretty darn fast. Okay. With my other power supply, this thing won't spin it fast. So let me turn it off. Okay. And let me disconnect this from the power supply. I'm going to bring it closer to the camera so you can take a good look at it. Okay. So there's the motor. And so this part is the armature. Okay, so basically all you have is a loop of wire rotating in this magnetic field. That's all it is. That's how you have to think about it. Okay, and these are the brushes. These make nice contacts because it's nice stiff metal. Probably something you might want to try to use when you're building your motor, something a little stiffer than the wires you're given. Okay. Now, one important item on this motor, it's really important. You notice how it's split there? Do you see how the 2 conductors? That's really important for a DC motor. Okay? You have to have that in a DC motor. This is the commutator. This is called a split ring commutator. Because if you don't have that, when the coil flips by 180 degrees, the torque will go in the opposite direction, and then the motor will just go back and forth. By splitting this, like so, once this thing goes through a 180 degree change, it'll reverse the current in the loop, keeping the torque in the same direction.
Is that like the cyclotron?
Yeah, the only case in this, you're reversing the polarity of the there you're just changing the voltage, right? Here you're changing the direction of the current. But yeah, you're right. So you need to have that. Now, if this were running on AC power, then I would have one of the brushes here and the other brush here, and that's it. And it would just run, no problem. But because it's DC, the current doesn't change direction, then I have to split the ring. This is a split ring commutator. Okay? So when you're building your motor, you'll notice in the instructions you're going to build a split ring commutator because of that. And so notice that when in this orientation, the normal to the loop is parallel to the magnetic field. All right? The normal to the loop, this is a loop of wire, the normal's that way. Okay, so there's no torque in that orientation. The torque is maximum here because the normal to the loop of wire is straight up, coming towards us. The magnetic field, if I rotate it like this, is either top to bottom or bottom to top. Okay? And so the torque is a maximum. Because remember, in the cross product, when the two vectors are perpendicular to each other, the value of the cross product is maximized. Because this thing constantly rotates, the magnitude of the torque product, the cross product, is constantly changing. You need to think about that when you're building your motor. Okay? You need to think about when the torque is a maximum in your motor, when's a minimum. You need to understand that. Okay? That's going to help you to make sure that this darn thing works when you build it. All right? Any questions on it? So the armature in the motor is what does the work. It is what transfers the energy from the system to the environment. Oops. And there's a lot of videos online on how a motor works, but there's very few on this type of motor. I did for the lab. If you look at the lab discussion, there's videos on pretty much the device you're building. Okay? You look in the modules and in discussion, you'll see videos on this motor. So please check those out. So, and I would, after the DC circuit lab, I would focus on building that motor. Because I know the DC circuit lab is going to take you some time. So focus on that first. And then start building your motor. I'm hoping it's a fun little project. So again, the motor consists of an armature, which is basically a coil of wire mounted on the cylinder. It is the device, the piece of the device that does mechanical work. The commutator and the brushes are stationary contacts that rub against, the brushes are stationary contacts that rub against the commutator that transmits the electrical energy to the commutator. To the armature. And the split ring commutator is designed so that the current changes directions when the loop flips by 180 degrees. If you didn't have that, the motor would just oscillate back and forth. It would be useless. I just want to say one thing. I just want to talk briefly about one important effect. I don't want to spend a lot of time on it because I never have a lot of time to go through it. Suppose you have a flat current-carrying conductor in a magnetic field. So this is the last thing in the chapter. There's a lot of applications of stuff in this chapter. Suppose you have a flat current-carrying wire, a conductor, not a wire, but just a conductor in a magnetic field. This is actually an important effect, and there have been similar, analogous, I guess, versions of this effect discovered over the years that have won Nobel Prizes. So let's say I have a conductor. And the conductor is carrying current in this direction. Okay? And we have a magnetic field into the board. So we have a magnetic field into the board, and we have a current this direction. So, meaning the electrons are moving to the left. So electrons, the current is going to the right, the electrons are moving to the left. They're drifting to the left. There will be a force on the electrons upwards. Making the electrons reach this end, leaving a positive charge down here. So what will happen is, when you have this conductor with the current going in that direction, you're going to have a separation of charge. You're going to have a bunch of minuses up here, and a bunch of excess positive charge left over. Now, I'm using a very crude model to describe this. The model is, the reality is much more complicated than this, because these charges are actually going to be kind of forced in a circle. And I'm not going to go through the complicated model. I'm just going to do a simple description. When this happens, then, you have an electric field that's produced because of this separation of charge that points upward. You have an electric field that points like this. And it's uniform. Okay. In fact, once this happens, the total force on the electrons is the electric force on the electrons is balanced out by the magnetic force on the electrons, and so we can get Q times E equals to QVB, because they're all perpendicular to these are all perpendicular to each other, and so E is equal to V times B, and these are the drift velocity of the electrons. This field is uniform because the magnetic field is uniform. If this separation is D, and remember that E, the magnitude of the electric field, when it's uniform, is the potential difference divided by the separation. So delta V is E times D. So we're going to actually have a potential difference between these 2 points. If the electric field points this way, then this is going to be a lower potential. That'll be at a higher potential. And this is called the Hall voltage. So you'll actually, it's a small voltage, but you can measure a small voltage between the two ends. And you can characterize, if you know the characteristics of your material, you can actually use the Hall effect and the model for current to determine, for example, the number of charge carriers per unit volume in your conductor. You can use the Hall effect to determine whether it's the electrons or the positive charge that are moving in the wire. That's why this effect is important. Okay? So you can measure the drift velocity of the electrons. You can measure the number of charge carriers per unit volume. And you can use now this property to measure magnetic fields. Once you can use the Hall effect to measure the various properties of materials in a magnetic field. You can use the Hall effect now to measure magnetic field. And materials that are used to magnetic fields are called Hall probes. Okay, so I'm going to stop there. And I have a video in the modules that discusses the Hall effect. And there's also a quantum Hall effect and a fractional quantum Hall effect. Okay. There's been a lot of research done on this topic. Of course, we don't have time to discuss it. If you were in solid state physics, condensed matter physics, you would spend a lot of time discussing this. So that's all I have to say for chapter 29. So I'm going to start on chapter 30. And in chapter 30, the focus of chapter 30 is to calculate magnetic fields due to wires. Okay. And one thing I forgot I didn't bring in today is a demonstration showing you that current carrying wires produce magnetic fields. I apologize, I completely forgot. I'm going to have to bring one in next time. Oops, what happened? Oops. Oh, sorry, I messed up. Okay. So we're gonna the goal of this chapter is to talk about sources of magnetic fields. Again, because of time, I'm not going to focus on magnetic materials. There is a nice discussion in your textbook. I highly encourage you to read it. I mean, I did say something earlier about the source of magnetic fields is due to spin of electrons. But unfortunately, I just don't have time to get into the details to discuss that. It's an interesting topic. That's why I'm saying read about it, okay? I'm really going to focus on sources of magnetic fields due to current carrying wires, because we can do a lot of those calculations. And so we're going to focus on the Biot-Savart law and Ampere's law in this chapter. And so the first thing I want to talk about is the Biot-Savart law. So many years ago, Ørsted showed that a current carrying wire produces a magnetic field. If you put a compass next to a current carrying wire, you will notice the compass deflect. And the magnetic field for a current carrying wire, like the one you see in a slide, circulates around the wire. The field lines form circles around the wire. Biot and Savart conducted experiments to study the magnetic field due to charges and infinitesimal lengths of wire. So let me write down some things they come up with. The field, the magnetic field due to a moving charge, let's say I have a charge, positive charge Q, I'll just put a plus sign, moving in that direction. And we normally don't do problems with this, but the field due to a charge, the magnitude is written in the following way. Q, V, sine of theta, divided by 4 pi r squared times some constant mu naught. Mu naught is called the permeability of free space. And mu naught, its value is 4 pi times 10 to the minus 7 Tesla amps per meter. The direction of this field is perpendicular to V. Okay. So let's say I wanted to calculate the field due to this guy at this location. This r is this distance. It's the magnitude of the vector that points from here to this point in space. If I wanted to write this as a vector, it turns out we can write it as a cross product. Where r hat is the unit vector that points from the source, that's directed from the source to the point in which you're calculating the field. That's our r hat vector. It's the same r hat vector we use for the electric field. So again, we're going to be learning how to calculate magnetic fields, just like we calculate electric fields. But I think these are going to be a little bit easier for you, in part because there's less problems I can have you solve, because the geometry gets difficult. So this is the field due to a charge. Okay. What about the field due to a current carrying wire? Well, Biot and Savart showed that if you have a current carrying wire like that, a lot of times the term filamentary is used, and let's look at a DS, and you want to calculate the field at this point. Okay, you define your unit vector r hat like this. And of course, the vector r is this vector also. It's in the same direction as r hat. The expression you get for the field due to this little piece is the current times ds cross r hat. Let me rewrite that. I forgot a couple constants. Mu naught or 4 pi I ds cross r hat over r squared. That's the field due to an element of the wire. The B field is perpendicular to both your ds and your r hat. The B field is, the magnitude dB is proportional to 1 over r squared. It's proportional to the current, its magnitude is proportional to ds, and it's proportional to the sine of the angle between ds and r hat. And again, mu naught is 4 pi times 10 to the minus 7 Tesla, oops, I had it backwards, Tesla meter per amp, sorry. Okay. I had it backwards before. It's Tesla meter per amp. And this is the Biot-Savart law. And it allows us to calculate the magnetic field for current carrying wires. Okay. Now, this is the analog of epsilon naught. So this is the magnetic analog . And in fact, it turns out that 1 over mu naught epsilon naught is equal to the speed of light squared. Maxwell showed that. Okay. So now what we're going to do is talk a little bit about. I might go a couple of minutes over, because I want to do one example, and then I'll do some more examples. I'll probably do more examples on Friday in lab. I'm going to use a lab Friday to do some more examples. Okay. And we'll do those in person, which is probably nice. Okay, so how do we use this to calculate the magnetic field due to the whole wire? Well, I have to integrate this over the entire length of the wire to calculate B. So again, like I did for electric field, I wrote down for you a process that we can use to calculate the magnetic field from the Biot-Savart law. To do this, you have to write an appropriate expression for ds. You have to write an appropriate expression for r, the vector that points from the source to the, r hat, the unit vector that points from the ds to your point P. You got to find the magnitude of r squared. You got to calculate the cross product ds cross r, and then you have to integrate for dB. You have to integrate dB. Now, be careful, you can use symmetry arguments to make life easier for yourself. So when you're solving problems, and I'm going to have a worksheet for this calculation too. So even chapter 30 has a worksheet. It'll be your last worksheet of the semester, okay? But I have one because you need to practice using the Biot-Savart law. Some of the problems in the chapter really are too simple for you to see how you use the Biot-Savart law, because some of them you can just memorize things and just apply it. So I want to do and by the way, this example is really easy and I can do this really fast, but I want to spend time going over it. So suppose I have a loop of wire carrying current like you see in the picture. Okay? And I want to calculate the magnetic field at the center of the loop. This problem is different from if I were to calculate the electric field due to a charged loop of wire, the answer at the center would be 0, but this is different. So let me draw a picture of this system, and I'm going to keep this equation on the board. By the way, I'm probably going to give you a couple extra days on the chapter 29 homework because I think I have it due tomorrow night. Okay? All right, so let me draw a picture. I have a current carrying wire. The current's clockwise. And my coordinate system, for some reason I changed coordinate system in the chapter. I don't know why I did that. Sorry. So my coordinate system, x, y, z. Okay. So this is the YZ plane. Okay. The loop is in the YZ plane. Okay. So my current's is clockwise. And I need to determine this guy, and this guy, take the cross product and integrate. How do I write my ds? Well, here's an element of the wire ds. This is the angle theta. My current, at that point, it points this way. Let me draw another coordinate system up here. This is z, this is y. Okay. What's this angle?
-90 minus theta. Wait, no.
Well, this angle is 90 minus theta, right? Isn't it true?
Yeah, and then the other one should be theta then, right?
Yeah, so this is theta. Actually, I'm using phi, so I'm sorry. Well, this is phi, and this is 90 minus phi, right? And so the magnitude of ds, like before, is just the radius of this thing times d theta. The vector is r d theta. The y component is going to be cosine of 90, and I keep saying theta, sorry. They're phi's. And the z component but what's cosine of 90 minus phi?
Sine of 90.
Looks okay so far? And r hat is the unit vector that points from this element to the center of the circle. So r hat points this way. R hat is minus cosine of phi j hat minus sine of phi k hat. All right, this vector points in the third quadrant. So far, so good. Okay. And r squared, that one's easy. It's just the radius squared. My next job is to calculate this cross product. I need to take the cross product of this with this. So I actually have to go through and do the following. And I'll tell you in a second, you don't have to do this. You don't have to do this, and here's the reason. To determine the direction of the magnetic field due to a current carrying wire, you can always use the right-hand rule. This is another one. How many right-hand rules are we there at now? 3?
I think so.
Okay, so this is the third right-hand rule. Because the magnetic field lines always curl around the wire, you point your thumb in the direction of the current, and your fingers will curl in the direction of the magnetic field. So my fingers will curl in the direction of the magnetic field. In fact, at the center of the wire, the magnetic field will point straight into the board. No matter where I go around the wire, the magnetic field will point straight into the board. So really, I don't need to calculate this cross product. This cross product gives me the direction of the magnetic field. I know the cross product is going to be into the board, the minus I hat direction. And if I evaluate that cross product, that's what I'll get, because I'm going to get minus sine squared minus cosine squared, which is minus 1. And so that cross product is going to give me minus r d phi I hat. And if you don't believe me, then do the cross product, do it the hard way. I just use symmetry. I know that all the way around here, when I apply the right-hand rule, the field points into the board. That's my ds cross r hat. So now, setting this up is easy. Mu naught over 4 pi times I. My ds cross r hat is minus r d phi I hat over r squared. Now I'm going to integrate this to get b. What are my limits of integration? I got to go all the way around the circle, so I got to go from 0 to 2 pi. So when I integrate this from all the way around the circle, I'm going to get mu naught I over 2r in the minus I hat direction, and I'm done. What if I had half a circle? What if I had half a circle? If I had half a circle, then I would integrate 0 to pi, and I would get half of this value. If I had a sixth of the circle, then I'd have a sixth of this value. Does that make sense? So this is not a hard problem. Make sure, absolutely make sure you know how to do these problems. Whether it's a full circle, half circle, quarter circle, or whatever. Make sure you know how to solve that problem. I said before, there's not that many versions of this problem that we can do. So absolutely learn how to do this from the beginning to end. Understood?
Yeah.
Okay.
Yeah.
So this problem isn't too bad. So if I give you this problem, where I only had 1/6 of the circle, I would do the same process, and instead of integrating from 0 to 2 pi, I'm going to integrate from 0 to pi over 3. And then in this particular case, I'm going to get b is mu naught I minus mu naught I over 12r I hat, if I say I hat is into the board. Okay? Because in this particular problem, I go through the whole same process, and I get, I just have 1/6 of the circle. On Friday in lab, I'm going to do a couple more examples. Okay? I'm going to stop here because I went a little bit over. So you folks have a good rest of the week. I'll see you on either Thursday, if you come to office,